Good afternoon. I am Dr. Obula Reddy, Associate Professor, Mechanical Department, BVRIT, Narsapur campus. Today, we are discussing computational fluid dynamics subject, its basics and industrial applications. Mainly present for mechanical engineering students, there is a important software tools, especially in the thermal engineering subject point of view. We have ANSYS workbench and also space climb, COMSOL, multiphysics. There are different softwares are available in the market. All these softwares, they have been developed based on this computational fluid dynamics subject, because this name itself clearly indicates that computational means we are solving, we are computing something governing equations. Fluid dynamics means we might study it in the fluid mechanics and advanced fluid mechanics, right? Law of conservation of mass and the continuity equation and the Bernoulli's equation, momentum equation, all these equations govern the fluid flow. Now, this computational fluid dynamics means we are solving those governing equations with the help of some computational tools. That is what, like ANSYS workbench, COMSOL and multiphysics, even space climb, then Siemens. There are different star CCM plus, there are different softwares are there. Using those tools, we can solve the CFD problems. In today's session, we are going to present, actually this lecture is as a part of Atal faculty development, Atal sponsored faculty development program. Now this title of this today's lecture is especially related to industrial applications. Now CFD can be applied in industry, many industry where the flow is there. CFD can be applied. This is simple logic, not only related to mechanical engineering, particularly like in the chemical industry, in the pharma industry, biomedical industry, like civil engineers. In the any industry where the flow related applications are there, where we can apply this concept computational fluid dynamics. This is basically used for the optimization of the process, like in geometrical perspective or either maybe like in the flow process perspective. In any manner, finally we need to bring out its efficiency, some more increased efficiency. That is what the intention of the CFD. Now in today's concept, we are applying this computational fluid dynamics especially for the ceramic industry, ceramic roller hot kiln combustion chamber with a preheated air from the kiln flue gases. Sir, actually, what is ceramic roller hot kiln? In the ceramic roller hot kiln, actually, say for example, if you are going to consider ceramic industry or any maybe tiles industry or something like any brick manufacturing industry, how they are going to manufacture the tiles or the bricks is initially from the clay. They will take the clay from that some mud, like some humidity of the clay they will take, then they will process in the form of some biscuits, like it is consists of some humidity content in that. Then after that it will be dry. They will dry that these biscuits, these are the samples of that tiles. They will make it heat treatment process. That is nothing but a kiln. Kiln is nothing but a combustion chamber. Where these biscuits, tiles will undergoes to heat treatment process. Now, what is the problem in the ceramic industry is, for heat treatment process, almost they are consuming out of total industry, if they are consuming 100% of energy, in that 60 to 70% of energy they are consuming just for the heat treatment process. There is a huge cost involved for heat treatment of the tiles or bricks or maybe something during the ceramic industry. That is why in this lecture, from the kiln combustion chamber itself, the flue gases are going out. By reutilizing those exhaust heat or the waste heat which is passed away from the flue gases, by utilizing that heat, how best we can improve the combustion efficiency using computational fluid dynamics. That is what they study in today's concept, reutilization of the waste heat. That is the main simple logic. Now this is the contents, like introduction part. We will come to know that what is exactly the ceramic industry. and what is the problem statement, kiln, what is combustion chamber, what is happening actually, that you will come to know. In the literature summary, we can discuss what are the various as of now till date in that perspective, like in the improvement aspect, what are the various research has been taken place as of now. That part we can see in the literature summary. And the objectives, after seeing that a lot of literature, we need to frame some objectives, like in the problem statements, what can be done, further improvement. Those things is nothing but objectives. Next, methodology means to solve or to achieve those objectives, what to be done in how we are going to do it. That is what is nothing but methodology part. In the methodology, clearly we can explain how we are going to solve the problem in a detailed procedure. That is nothing but methodology. In the results and discussion section, we will get some results. Those results and discussion section, we will see that all the results, different using CFD, what are the results, that part we can explore. And next one is the last conclusion. From this problem, what is the final conclusion, that one we'll see. Now coming to introduction, you can see that there are beautiful images of the kiln. The first topmost images are all the combustion plant for these are all the kiln photographs we have taken from the Vennar ceramic industry. Like physically I visited that Vennar ceramic industry, then I took that some of the photographs. These are the some of the pictures. Then next below we can see that this diagram is nothing but kiln from the beginning. This is the pre-kiln eco redox technology. From here, this is the tile is entrance. Here entry part is there. This is the entry, and corresponding this is the exit. This is the exit, final cooling. Actually at the entry you can see that this red color is slowly increasing. This red color is slowly increasing means this is clearly indicating that the temperature is increases. The temperature curve is like this. The temperature is increases. Maybe here at the entry, maybe the normal temperature, but when you are keep on moving to the next, these are the chambers like modules. These are all called as module 1. This is module 2, module 3, module 4, module 5, module 6, module 7, module 8, module 9. 7, 8, 9, 10, like that. There are different modules are there. When you are moving just inside, like when the tiles are moving inside the combustion chamber, then temperature also increases like this. That is why this graph is indicating that when you are keep on moving to the another module, the temperature is increases. Here the maximum temperature is almost 1300 degrees centigrade. This is the 1300 degrees centigrade temperature. Up to that temperature we will heat the tile, so that we are getting some strength, some hardness, the required hardness and the required brittle strength will establish for that tile. Okay, that is what this is the tin flame burners. These are all called as, here we are providing some burners either that side and this side. Like if you are going to cut this section, exactly we can see that this is a shape of the bus. If you are going to imagine that the ordinary bus is there, like transport, like state transport buses are there. If you are cutting some section, exactly section, in the similar manner it is there. On that left side some burner will be there, right side some burners will be there. We are supplying the fuel and the air so that the combustion will take place. That part is here. Inside, as that combustion is taking place, these tiles are subjected to those hot flue gases. That is how the tile is being heated. The next one is the heat recovery part. Here there is one concept, heat recovery part. Here what we are doing is we are extracting, that means some hot air we are producing. We are extracting that waste heat. We are extracting that waste heat, and the next one is slowly we are cooling that tiles. After bringing to the 1300 degrees centigrade, by the end, when this tile is coming outside of this kiln, we need to cool slowly. All of a sudden, we should not cool. We are decreasing its temperature again slowly up to room temperature, so that the tile will establish the required strength. Now here there is one table. In this table you can see that in the pre-combustion zone is there are different zones are there. In the pre-kiln zone, the temperature is 200 to 225. This is the pre-kiln zone. Temperature is 200 to 225 degrees Celsius. Next is the preheating zone. The temperature is this one, like 550 to 1120 degrees centigrade. Next, firing zone. This is the main firing zone where the burners are there. Here the temperature is 1445 to 1175 degrees Celsius. Next one is the rapid cooling zone where we are decreasing rapid cooling, almost 1200 to we reduce it to the 650. It is 1200 to 600 is half of the temperature is reduced in this zone. This is nothing but rapid cooling. Next one is the slow cooling zone. And the last one is the final cooling zone is 375 to 65. So that finally we are reducing to the normal temperatures, to the room temperature. This is what the kiln is. In the ceramic, why it is called as ceramic kiln means using this kiln we are producing the tiles, ceramic tiles. Okay, at the entry here the humidity tile like mud, soil in the form of biscuits will enter inside. It is consists of like full of water content is there inside. So that when it is subjected to high temperature, slowly that water vapor will become evaporate, that the porosity will form within the tile. Whenever if you break the tile and if you see it inside, small, very small holes will be there, like it's a porosity. It depends upon the type of material also, how best that porosity, all those things will establish. Okay, now here if you are observing this concept, sir, we are that means utilizing lot of heat here to heat the tiles. That is the main and most important function or the process and the complex process as well in the ceramic industry, and where we are contributing lot of investment also in this aspect for this only. So suppose if we are going to introduce any new technology which can bring out these investment, then almost the tile cost will reduces drastically. Actually, suppose if the tile is almost 10 rupees per tile, like that in that case, here out of this 10 rupees, almost 6 rupees are used for the heat treatment. Like we are purchasing the natural gas. So what is the fuel over here? We are using the natural gas. Using that natural gas burners, by burning the natural gas, we are producing the inside hot environment. That is why only per tile almost 6 rupees and 60% is used for the heat treatment process. Okay, that is what the actual story. Now today a problem we are going to see. This is the total whatever I explained in the diagram itself. This is the everything. Okay, here in the point wise I have been given everything. You can go through it. Like in the second point, compared to the ceramic plant's total energy consumption, kiln title, that means title firing takes more than 50% of the energy. This is what I told. Like more than say 50% means I consider as 60% almost. According to the 2017 statistics, almost 8,000 ceramic kiln produce tiles after the firing process. After the firing process only, they will produce the tiles. The analysis of everyday average energy consumption for the kiln in 2011 found that like worldwide there is a total consumption of 1.8 into 10 power 5 gigawatt hour for natural gas. This much of the huge amount of the natural gas they are consuming for the production of these tiles. Like the process of ceramic tile manufacturing with the different stages of material processing, processing of the pre-fire tiles, firing and glazing was discussed in this literature 4 and 5. If you go through these literatures, you will come to know that what is exactly pre-processing and processing and firing processes. Now this is the literature summary. Problems identified, and left side is the problems identified. Then this is the research gaps to optimize the performance of the kiln section. If you go through some of the research articles which is completely related to the kiln operation and the kiln optimization and the kiln combustion chamber and the different burners and the different fuels which are used for the ceramic kiln industry, only if those research articles, if you read it, then you will come to know that what are the exactly problems identified. Now this is the first problem is the heat loss from the kiln side walls 60 to 70 degrees centigrade. Actually this is one problem. Now it is like as I told that in the beginning, this is the like section shape of this bus cross section. Like for LE is a combustion chamber. Combustion chamber means there is a wall will be there, combustion chamber wall. Now that wall outside temperature is almost 60 to 70 degrees centigrade will be there. Now the heat loss from the cooling air used for the cooling process through the chimney. Heat loss from the cooling air used for the cooling process through the chimney. The heat loss from the firing section with the flue gases through the chimney. The heat loss from the firing section through the flue gases through the chimney. Through the chimney also heat losses will be taken place. Next, burner can be optimized for the efficient combustion. Like the natural gas burner, whatever we are using currently, those burner can be improved, design optimized, can be optimized for the efficient combustion. Like with less fuel, we can reach over that complete combustion. Next, combustion phenomena to be studied, that to be investigated, like chemical kinetics. Next, expensive fuel for heating and firing process. This is also one problem. We are using the lot of fuel expensive for heating problem. Next, these are all the various problems identified related to ceramic kiln operation. Now, if you are coming this side, that research gaps, what are the gaps, or maybe that scope of improvement, that is what this thing, research gaps to optimize the performance of the kiln section. Energy conservation studies for the kiln efficiency improvement. Like this is a kiln is nothing but a chamber. For the chamber inside some fuel is and burning, like some heat we are taking. Some heat is utilized for the heat treatment process and the remaining is converted in the waste. Those that energy balance should be done in a proper way. So that as how best we are going to do the heat balance heat of the kiln, then we will come to know that where the losses are taking place. That is what this. Next, optimization of the kiln wall thermal insulation using CFD. Now, earlier here it is maintaining the 60 and 70 degrees centigrade, the kiln wall temperature. That can be reduced using some computational fluid dynamic studies, so that we can suggest that wall insulation, how best we need to provide to reduce this 60 to 70 from like further decrease that temperature. Optimization of combustion phenomena using CFD. Like using computational fluid dynamics, the inside combustion also can be further investigated. Like that is what in this class we have done it. Next, customized simulation based on the actual kiln designs. Customized simulation based on the actual kiln designs. So that for initially we will take that actual kiln design, like how many modules are there, how the burners are placed, what is the burner design. That is the actual kiln design. But we may suggest some more better designs based on the CFD investigation. That is what this point. CFD analysis for proper heat dissipation in the kiln enclosure and heat conduction through the moving tiles. Like a heat dissipation in the kiln enclosure and heat conduction through the moving tiles. As the like inside the kiln, there are some rollers like this. This pen how it is rotating over the as this is rotating over this, some tiles are there. The tiles are also moving. The tiles as moving from module 1, 2, 3 and so on and getting heated up. Okay, it is also carrying some heat that can also be investigated and we can like recover that heat. Optimize the working condition for better heating and cooling process. This is also one more important point. Like operating conditions, how you are operating. So that because this is having a huge length, it is consists of almost 300 feet almost will be there. 300 feet or 200 to 250 feet, that 200 to 250 feet length, that kiln. That much huge length, operating is a very big task, because we have to maintain at required module, the required temperature and the required pressure, like desired temperature and desired pressure for the better performance of the heat treatment. Like if you are not operating to the optimum condition, we are wasting more fuel. Either that can be taken place, or otherwise maybe that the tiles may be not heated properly up to the mark. These are the two problems. That is why operating conditions can be optimized. Analysis of fluid flow to understand the impact of new equipment settings on the existing setup, so that we can understand the fluid flow by changing the operating conditions or etc. These are all the various gaps. So from these gaps, we took one gap or maybe one scope for the further improvement. That is what we have done. That is what using computational fluid dynamics we investigated. The same thing I am explaining here. Now, if you are going to see on the left hand side, in this research, an attempt has been made to optimize the combustion process of the ceramic kiln section with the utilization of the waste heat recovery from the exhaust gases related to the released from the kiln section. Actually, in the beginning, whatever I shown that the kiln, this is the huge length is there. Inside combustion will takes place. After combustion, where that flue gases will go, that flue gases will released via chimney to the atmosphere. That means that is the waste heat. Now, what I am doing is here, that heat is used so that to heat the air which is entered inside the combustion chamber, so that the combustion efficiency will be improved. That is what exactly I am doing here. In this approach, an attempt has been made to optimize the combustion process of the ceramic kiln section with the utilization of the waste heat recovery from the exhaust gases released from the kiln section. Now this is the fuel inlet CH4 and this is the preheated air inlet from the kiln flue gases at different temperatures will be there. Like a preheated air, that means how from where this has been preheated, because this is preheated from the heat which is taken from the exhaust gases released from the kiln section. Okay, there we are getting that heat to preheat this air. Now this air is entered from here, this CH4 is entered. This is the like flame is there, flame dynamics, flame length and flame width. Here also this bottom burner, and this is the flame length and flame width. This is the kiln cross section. This is the completely kiln cross section. Okay, this is the tiles are there, like these are the tiles and this is the rollers. Okay, now this is the bottom burner and this is the like left burner and right burner, like top and bottom burners. This is the computational domain. This is the computational domain. This exhaust air consists of high internal energy, hence its effect has been studied with the different temperature and pressure inlet conditions to optimize the combustion process. The whole project has been executed numerically by considering the cross-sectional domain of the kiln. This exhaust air consists of high internal energy, hence its effect has been studied with a different temperature and pressure inlet condition to optimize the combustion process. Now this is the CFD methodology, like this is the pre-processing step and this is the solver part and this is the post-processing, and in between solver settings are there. This is the pre-processing, this is the solver part, like this is the solver setting and this is the post-processing. Like very simple, in the pre-processing geometry will be created. In the solver part we are setting all the numerical setup required. After that we will solve the iterations. Finally, in the post processor, after getting the results, we need to analyze those results. That is what the first processing we are doing. In the numerical modeling, the ceramic kiln combustion chamber computational domains are investigated numerically using the computational fluid dynamics tool. ANSYS Fluid 19.1 academic research version is there. It is available in our department. The flow governing has been resolved with the Reynolds average Navier-Stokes equation. In the beginning, I told you, like fluid dynamics, that fluid dynamics is controlled by the law of governing equations like continuity equation, momentum equation and energy equations. Okay, those equations thus we are going to write in the form of Reynolds average Navier-Stokes equations, RANS equation, called as RANS equations. Those RANS equation and the standard K-epsilon turbulence model and the eddy dissipation species transport reaction mechanism, eddy dissipation transport reaction mechanism for the combustion of methane air. This is what the complete setup of the governing equations we are considering, the background of the fluid dynamics. Now, using these all these governing equations, we are going to use the finite volume method. How we are going to solving that finite volume solver will be there in the background part. I am telling, like in the fluid, what is happening exactly in that tool. These partial differential governing equations like nonlinear forms are there, are converted into a set of linear equations using the finite volume method discretization technique. These complete linear Hollow equations are solved using the pressure-based solver with the simple algorithm like pressure-velocity coupling. Now, the standard different terms in the governing equation are converted into the different finite terms using the second order of wind discretization. As the kiln combustion chamber is exposed to higher temperature, 1200 degrees centigrade, the radiation effects are also considered. And model using surface to surface radiation model is used. This is the completely numerical modeling setup, like here the solver part, where I am using the solver part, that is what this numerical modeling section. Next, boundary conditions. For solving any governing equations, first initially we require some initial and boundary conditions. Now what are the boundary conditions? The fuel and air inlet boundary condition are defined with the Dirichlet boundary condition by specifying the known values of the flow stream for the respective air and fuel inlet conditions. Say for example, if you are going to consider any, like if you are seeing in the beginning here, like here some fuel is entry, this one is the fuel inlet and this is the fuel inlet, air inlet is there. At what velocity, at what mass flow rate is entering inside the combustion chamber, that part we will consider as a boundary conditions. That is what we are considering the boundary conditions. Now air inlet is there, air inlet and corresponding air inlet temperature, that is the air inlet mass flow rate, air inlet temperature, fuel inlet mass flow rate, fuel inlet temperature. Totally we consider the 6 cases. Now this is the case study problem. Sir, what is exactly that case study problem? As I told in the computational domain, some fuel is coming, some preheated air is coming. That preheated air at what temperatures? That is what the main motto of this problem. Now we are considering at different temperatures, air inlet temperature 27, 77, 127, 148, 175, 175. Now this is the preheated air temperatures. Different cases we have been considered. So that the better combustion will take place with less amount of the fuel. That is how we are saving the fuel which is actually required for the heat treatment process. So that if you are saving the more amount of fuel, that is how we are saving the economy. That is how we are saving the investment of the fuel investment on the kiln heat treatment process. That is what the exact research problem over here. Now different cases are considered. Now this is the grid independent study. Like in the grid independent study, this is the computational domain converted into the small grids, and these are the graphs, so that different cases, how by considering the different cases, we can see. And this is also another one is top burner experimental, bottom burner, and these are all the different burners. So that by considering the validation also we have done. Okay, here in the what is the validation means? Validation is nothing but for any numerical solver, for any numerical problem, if you are getting some numerical results, definitely that numerical results will be compared with either with the that means experimental, which is previously investigated experimental results, or maybe some theoretical results, so that how much deviation it is there. If it is the somewhat very less little variation, then we can consider that okay, we can proceed whatever the numerical methodology which we followed for getting these results. If these results are correct, closely matched with the experimental results, then I can believe our numerical methodology is right or up to the mark for investigating further problem. That is what the validation to be done. Grid independent study is nothing but, suppose these are all the grids. This is the mesh generation. Mesh and grid is similar. Suppose this is the mesh generation. Here I am going to consider the some size 1, size 2, size 3. Like that, if you are going to consider the more number of sizes, these mesh elements will vary. As you are changing the mesh elements, the results also will vary. But one fine movement, at a fine moment, if you are changing further that the size, results won't change. That is the point where that the grid optimization has been achieved. So that optimized grid can be considered for the rest of the problem. That is what the grid independent study. Now this is the results, where you can see that the results, this is the case 1 results, this is the case 2, case 3, case 4, case 5, and the case 6. Now in the total all 6 cases, because we considered in the boundary condition 6 cases are there. How we framed the 6 cases? Depending upon the air inlet temperature. This is the top burner, this is the bottom burner, and similarly here also top burner, bottom burner. This is the flame length and flame width. If you are observing that the 1, 2, 3 almost looks similar, like even that 4 also cases, but whereas case 5 and case 6 is somewhat decreases its flame length, it is not intensed up to the mark. Even this part also not up to the mark. Okay, that is what in this case. Now here the top burner axial temperature profile and the bottom burner axial temperature profile. Yeah, I am going to draw, like I am going to just consider the temperature parameter along the flame length, the top burner, and also along the bottom burner flame length. I will catch that how the temperature is varying along the length of the burner. That means along this in this direction for the bottom and top burner. Then I will take that values and draw the graph for 6 cases. This is how, like for the initial case 1 is these are the results, and the case 2 is here only, case 3 also here, case 4, case 5, case 6. It is decreasing in this manner if you are moving further. Here also the same story, but is the bottom burner is there. This is the bottom burner B, and this is the top burner A. Now these are the different cases. Next, cross stream temperature profile for the bottom burner. Cross stream temperature profile for the bottom burner. That means how I am going to draw it. If you are going to consider one location, different location, here also one location, at different locations like a cross stream, the flow is taking place like this from left to right. if you are drawing one graph over here, how it is being varying, that is what these graphs. Okay, for A and B is nothing but cross stream temperature profile for the top burner at A, this one, and B, this one, C. Top burner, this is the completely top burner temperature profile at a different locations. I am going to consider what is the different location: 0.25, 0.5, 1, 1.5. That means from the burner is the location. If I am going to draw that temperature profile, how it is been at the beginning, it is slightly less temperature, but the almost at a B, at this point, almost the temperature profile is nothing but like it is coming to closer. Okay, and that point is here. This is the bottom burner also. This is the bottom burner temperature profiles. Why we need to see all these temperature profiles? Because we are identifying the case which is having lesser fuel consumption but equivalently producing the same aspect. Like in the case 1 and 2, we are not that means sending that any preheated air. Directly we are taking a more fuel and getting the required temperature. But whereas the other cases, this is the situation where we are using the preheated air and considering the less amount of the fuel. Even though we need to achieve the initial temperatures, which is we are obtaining in the case 1 and 2, like that. That is the story. Now, these are the mass fraction profiles of CH4 and the CO2. This is the fuel and this is the byproduct. After combustion, we are going to get CO2 and H2O. This is the natural gas CH4. Initially, we are considering as a fuel. After combustion, we are going to get a H2O plus CO2. CH4 and CO2, we are getting the H2O and CO2. Well, these are all the various temperature profiles. Figure 8A. Top burner CH4 and CO2. CH4 and CO2. Next is the bottom burner CH4 and CO2. This is the CH4 and the CO2. This is the mass fraction profiles. Okay, this is decreasing. This is decreasing. Actually, the fuel is decreasing along the length of the flame, if you are seeing, because it is converted into the products. The fuel initially at the burner inlet, it may be completely mass fraction is 1. Let us, this is the higher value, mass fraction is 1 at here at this point. But when you are coming down, you are moving far away from the burner, that the mass fraction value is decreases. Almost at here it is the 0.025. It indicating that the fuel is converted into the CO2 and H2O. Combustion is taking place. That also we are considered for the different burners, different cases. This is the turbulent rate of reaction for the top and bottom burners also as well. In this case, case 4, like this is the case 3. Next, this is the like case 2, and this is something like case 1. Okay, different cases also we consider the turbulent rate of reaction for the top and bottom burner. The rate of reaction for the top and bottom burner for different air and fuel inlet condition is analyzed in figure 9. This is what for different burners. For the last 3 cases, 4, 5, 6, with increasing air fuel ratio and preheated air temperature, the maximum reaction rate of 0.8 mole per meter cube is identified with case 6 flow conditions. This found that even with the decreasing fuel intake, increasing preheated air temperature, the rate of reaction increases, which is favorable for efficient combustion. Actually, this is what main task we need to achieve. This is the tile surface temperature profile. This is the main where we are going to identify the required case with less fuel input. This is the different cases. Tile top surface, tile surface temperature profile. Okay, this is the tile surface temperature profiles. And this is the top burner, top surface, tile top surface, and this is the tile bottom surfaces temperature profile, and this is the average. This is the average surface. So that if you are going to consider average of this is the case. Now here we need to consider the case which is having almost 1, 2. Like this is the case 3 is here. Next case 2 is here, case 1. Case 1, 2 is the first, this case 1, 2 here. Now case 4 is almost in similar. Case 4 is almost this here, if you are observing. Case 4 is almost similar with the 1 and 2, the required temperatures. Very minute is the difference. But comparatively, there is a lot of fuel saving with the case 4 operating conditions. So that we are going to do the economy. This is the case 1 heat absorbed by the tile. Case 1 is this much. Case 2, case 3, case 4, case 5 and case 6. The heat absorbed by the tile is increases slightly from case 1 to case 3. operating condition due to its maximum combustion temperature with increasing fuel intake. However, case 4 has achieved the similar range of heat addition even with less fuel intake, heat recovered from the waste heat flue gases. This is 995 and this is 1016. There is no much difference in these two cases. Then what is the need? But compared to these three cases, we are taking the more fuel, but whereas here we are taking the less fuel. But how it is we are getting this much temperature? Because we are getting the waste heat in the form of preheated air, so that we are achieving this much maximum value very closely. Just it is a difference of 20 degree like that, the deviation. 20 degrees is not a matter. Here also it is not 20 degree. This is the something like 15 degree. Here also is very less, even compared to 10 degree. Okay. Now fuel economy. The amount of energy input for the kiln combustion chamber has been calculated for all the cases by evaluating the fuel input energy and the energy recovered from the waste heat flue gases as shown in the table 2. Now this we can consider like in the form of the waste heat, how much waste heat we are going to recovered from the flue gases for different cases, and during the same aspect how much fuel input we are utilizing for the different cases, that also to be calculated, and finally total energy also we are summing up. The waste heat case 1 is nothing but zero waste heat. That means we are not utilizing the waste heat which is passed away from the chimney. This is the fuel input energy, highest is there 14.248, and this is the same. In the case 2 we are using 0.365, and here it is a little increment total input, and here also same. Okay, this much is the waste heat, and finally this is the last case we are reducing the fuel input and we are increasing the waste heat. Here also we are increasing the waste heat. We are reducing further, increasing the waste heat recovery. So that finally this is 11.83, and what we are getting like that means as we are reducing the fuel input, next case we need to calculate how much fuel saving. Now the performance of the kiln combustion chamber, like here see comparatively case 4 the total input energy is almost equal to the first three cases even with the decreased fuel input energy. The same has been observed in the burner temperature profile also. Okay, that is the main point. So that finally we are decreasing the heat energy, like in the case 6, like case 4 is having less heat input energy. First case is 14.24, in this case 13.20. Now there is a difference, is there almost 1 kilowatts, that input 1 kilowatt energy is there. Now this conclusion is finally the performance of the kiln combustion chamber with the different fuel air inlet condition is assessed by analyzing the diffusion flame intensity using temperature contours and the profiles of the mass fraction and all those things, reaction rate and temperatures and as well as mass fraction and all those things. Now finally from the analysis the following key points has been identified. The kiln input energy is increasing without increasing the fuel consumption, but with recovery of waste heat from the kiln gases. That is the main point we achieved. The waste heat recovery energy enhances the reaction rate preheated kiln gases. The maximum reaction rate 0.8 has been observed. In the first three cases, the tile surface temperature profiles are well matched with the negligible temperature drop of 7 degree. The comparison of tile surface temperature profile found that the case 4 with less fuel intake also obtained the desired temperature range of this much. It is also noticed that the case 4 has similar quantities of profiles, like the energy consumption analysis found that the only case 4 has required less input energy than the first three cases, however developing the desired surface temperature profile for the tile heat treatment process. For one kiln combustion chamber with 15 firing modules, the fuel intake is this much, 103.67 kg has been saved per day with the case 4 operating conditions. Like for 15 firing module cases, the fuel intake of 103.67 kg of fuel per day has been saved. So that the amount of saving is nothing but 103.67 into corresponding price. That means price of this fuel input. So that this is the saving. This is how we are implementing this research problem has been investigated using computational fluid dynamics by recovering the waste heat which is passed away through the chimney gases for preheating of the air. This is the problem using computational fluid dynamics. If is there any doubts, you can approach me. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.